yeah.
Oh. Where is the clicker? Oh, yes.
There you go. This is a data cube. Inside of it, embedded is something interesting, whether it's a person or a theory or an equation. But you can marginalize that interesting object into different planes. And sometimes those planes are more valuable than others. And if you were trying to interpret what this person was or this object, you might look at this plane and think that it's about George. I'm not going to throw it at you. This,
We're not sharing our screen.
we're not sharing our screen.
We're not sharing our screen.
Freeze.
That one is the controls. Okay, I think that's.
This is another interesting object, which you can project in many ways onto a plane. This object was $1.79. This object projected some years ago, you can buy, no, forward. You can purchase one of these. I was going to try and get you one as a present.
Well, you could give me that one.
All right. But it was $11.6 million when it last sold at Sotheby's. You've lost a lot of information by projecting it. You've lost all the ingredients. You don't know how to open it. You don't know what's inside. And yet it's a privileged projection. This is a data cube for variable stars. That's the preferred target, the equation at the top, which is a version of the Stefan-Boltzmann equation, where we've replaced the radius with the period of the star. It is a period luminosity relation plane fitting in a three-dimensional volume. And the projection of that plane onto various surfaces, either in a period luminosity relationship or color magnitude relationship, they have certain privileges and worth to them, to the point that the period luminosity relation actually has a name for the Cepheids. It's the Leavitt law. That's the diagram that you think of when you project the PLC into that plane. This is the Hertzsprung-Russell diagram for the instability strip, and you think of it when it's projected in that. But these are all projections of this one fundamental equation. Comfortable with 2, 3 dimensions? Now think about 6, 7, or 8 dimensions and think of their projections onto any one of those planes. Some of those dimensions are the Bailey diagrams, Osterhoff group, Sturge's law, period shift effect, period amplitude dichotomy, Stefan-Boltzmann's equation, the instability strip, and the period luminosity relation. Bailey's law, have to go back to 1919, a little bit before your time. But Bailey had only 2 things to plot, a period against an amplitude, so it was natural to plot it on a piece of paper rather than a 3-dimensional frame. These things, turns out, those are the overtone pulsators, not really interesting. And there's not much to be said about what's left over there, except if you happen to be Osterhoff 20 years later or so, who had yet another parameter to plot his periods against, and that was metallicity. He found that there was either, is the primary physics in this gap, or is there primary physics in the fact that there are 2 populations? Nonetheless, it bears his name. It's a projection from this higher order space in which a lot of information resides And I'm trying to bring it all together into one plot for you at the end and explain it all. Here are now Bailey diagrams in a much more high definition mode, where there are two different globular clusters, M3 and omega sen, which represent different metallicities. And again, it's amplitude versus period, and you've got the dichotomy there. But what about this thing called Sturge's law? Conrad Sturge, somebody, he's smiling. Conrad Sturge in 1966 went into George's office and said, "Do you have a thesis for me to work on?" And George said, "Go measure UBV photometry of our Lyra stars and come back in a couple of years and tell me what you found." Well, what he found was that the colors of our Lyra stars at minimum light, they all have the same color. There's a little bit of a trend with period, but they all have the same color. And he just pointed that out as an interesting tool, an interesting way of determining reddenings to our Lyra stars, because you use the fact that this is fairly constant. There's a little bit of a trend with period. That's independent of distance. You plug it in, you've got the intrinsic color at minimum light, subtract that, and you've got your color excess. So he said at the end, "I wish to extend my thanks to Dr. George W. Preston, who suggested this project." Well, he's back to haunt you. Okay. So I want you to burn this into your memory. This is the Bailey diagram and the two Osterhoff types, 1A, and I've just chunked off bits and pieces of this as you go down. And a little hint as to what's coming. This is the blue edge. This is the red edge, faint edge, bright edge of this projection, if you were to see it where color or luminosity were part of the equation in this multidimensional data
What are
cube.
the A, B, and C's in there? I didn't get.
I'm going to show you what they are a little bit later. They're just
Okay.
markers to
Oh,
run you across this diagram. Okay. This is the same data cube now, where it's luminosity versus color in this plane. So this is the instability strip, which we saw in the previous talk. These are samples of lines of constant magnitude here. And then there's lines of constant color, and they're all projected in here. They're hiding. So anything that isn't color and luminosity is hiding as an implicit variable in here. So there are period lines up and down this instability strip. But this instability strip is not defined by the period luminosity color relation, this plane, because it's infinitely defined. There's nothing in that equation that I showed you that said you stop here, you start here, you stop there. It's just totally ignorant of what the other physics is, and that other physics in here, ta-da, are two independent constraints on the primary equation filling the plane. On one hand, you have the blue edge of the instability strip, which is defined by physics of the interior and where the helium ionization layer occurs. The other is totally independent physics defining the red edge, where pulsation is overwhelmed by convection. And then the definition of the period luminosity relation in that perspective is that ridge line going through between, and is defined by the two constraints on the period luminosity color relation. Okay. Here now, I've swung it in. This is now the period luminosity relation, and here's our control equation. And here is a line of constant magnitude. Now, nobody would claim that that line there is the period luminosity relation. One thing that I didn't point out was that in order observationally to define the period luminosity relation, you want to put data points as uniformly through this surface in order to get the ridge line determined observationally. And that ain't it. Okay. May seem subtle, but in a paper by Catalan, Pritzel, and Horace, entitled The R.R. Lyry Period Luminosity Relation, Theoretical Calibration, this is the amazing plot that they came up with from their theoretical calculations of what's going on for R. Lyry stars and other stars across the instability strip at the level of the horizontal branch. And here they managed to throw all of these things above the concentration out and run regressions on these PL relations. So here we are in the U, downsloping the B, flat and visual, okay, that's what we expected. There's not supposed to be any PL relation for the visual R. Lyry stars. Doesn't mean that there isn't one, it just means that the coefficient is 0. And then the coefficient picks up in the R, the I, J, and you notice also in the process of this slanting up, the relationship is getting narrower, the dispersion is being suppressed, and these are great regions to be doing PL relations to do distances. Marcio was willing to send me the data, and this, in fact, is what the result is. Same data, totally different interpretation. As you saw, the PL relation is defined by the red edge and the blue edge of the distributions, and these are those lines. This is the instability strip going up into the color magnitude diagram, if you like, but as seen in the period luminosity relations. Same thing, everything's happening to the data as in the other plot, but interpreting it is very different. And it's good to get a perspective on it by backing away and taking a look at the entire data set that was available. And these are the stars that are contributing to the color magnitude diagram now, color down here, magnitude here. In the ultraviolet, here's the blue horizontal branch, if you want to call it that, as things rain down from the tip of the red giant branch. Here are the stars that we saw before in the instability strip with a negative slope. Flatten the slope, increase the slope, stars coming in and above the horizontal branch, producing yet another sequence. You can see them coming across here as there. So this is what people naturally were inclined to say are the PL relations for R. Lyry stars. It's not true. These are the PL relations for R. Lyry stars and all of the stars above the plane as well. And how can I say that with any confidence? Well, we're back to this plane, the color plane, period, luminosity, a selection of stars coming from a horizontal branch. Here's the blue edge, red edge, horizontal branch stars going across here at constant magnitude. And this is the PL relation. This is not the PL relation. Now, what if I were to say, well, okay, I'm going to now put in another little slice of sample of stars up there, not at constant magnitude, but just provocatively here. This now is the implications of Sturge's law and that little extra that I put in. Sturge's law tells you that there is a very small dispersion region where every star at its minimum in its light curve reaches and has the same color. So a star here, which has a large amplitude, will find itself here at mean light. Another star here of smaller amplitude will find itself there. And similarly, as you go down here, and if there are two of these regions that are being populated, one by stars landing on the horizontal branch, they will have their amplitudes increase as a function of color and as a function of period. These will also have a parallel sequence of increasing amplitude as you go to decreasing period and decreasing color. All the consequence of Sturge's law being imposed on the properties of the instability strip. Now, well, you might ask, well, is there more to it than that? Here's the control equation. Is it really true that the color, the intrinsic temperature, is controlling all of the scatter in those plots, which they just threw away when they were making a fit to the horizontal branch? So the one test is you, without destroying anything, you just move that term over here. And now this says whatever this thing is, this W, which is a function of visual magnitude and color, modulated by the physics of the color and the intrinsic temperature, is now predicted to be strictly a function of period. So all of the scatter in the PL relation will have disappeared, and all you'll be left with is the period. And here is the result of doing that calculation on that data set for all of the stars, not the ones just on the horizontal branch, but everything up and above it. Okay. These are the last two slides. Coming back to the schematic of the Bailey diagram, can we incorporate that into the PL relation or the color magnitude diagram relation in a seamless way? Here it is beside. Here are those numbers you were asking about, George. Here they are again over here. And it only takes, if you're a little bit confused, this should help it. I've tipped that diagram. And okay, there it is. Type 2 Osterhoff group stars are this upper channel of stars coming off the blue horizontal branch, coming in high and coming across. These stars on the horizontal branch are the type 1 Osterhoff stars. So if you don't have a blue horizontal branch, you don't get any of these stars contributing to the Osterhoff type 2 for that particular globular cluster. So this is it. This is the visual conclusion that this is now 5 or 7 dimensions projected onto the color magnitude plane, which incorporates Sturge's law, blue horizontal branch, red horizontal branch, Arillary stars, stars supra the horizontal branch, transiting across and up into the pre-AGB. And thank you for having Conrad Sturge come into your office and you just didn't kick him out. Oh yeah, you don't want to hear anything more from me.
My mind,
Well,
thank you. All right, so we do have one question from Horace online. Can you go ahead and ask your question, Horace?
Yes, very interesting talk and a way of looking at that diagram that I had not thought about before. One of the predictions would be that the stars that fall into the Ostrov 2 category should have larger rates of period change than those, and those periods should be mainly increasing compared to the Ostrov 1 stars. just like you saw in the diagram from Marcio for globular clusters as a whole. So that should be testable.
I agree. They're in the right place and they're.
Oh, sorry.
Sorry. I agree. They're in the right place and they're in the right evolutionary state to be monodirectional. There will be a little bit of confusion down on the horizontal branch, don't forget, because in evolving off of the horizontal branch, there's a rapid transition towards the blue, and then they hook back and they also start moving towards the red and onto the horizontal branch themselves. But the horizontal branch is the real horizontal branch is always offset from the pseudo horizontal branch, which is the type 2 Osterhoff group stars.
There's actually a question, another question online from Giuseppe. Why don't you go ahead and ask your question next, Giuseppe, and then we'll get to the questions that are here in the audience.
Okay. So very interesting talk, but I have a curiosity. The problem is, in my opinion, that the loops of the variables is not constant across the instability strip, in the sense that the theory and observations are suggesting that the slope is becoming almost vertical as soon as you approach the red edge of the instability strip. And probably this might not be a problem. This is just one of the possibilities why the Sturge's law doesn't work. Because we know that it doesn't work. It's just a first approximation. But if you would like to do the things in detail, you will realize that this is not what the nature decided to do. In particular, I would say, for those ones that are not large amplitude pulsators, there is a trend, there is a drift in these empirical laws suggested a long time ago. What do you think?
I sort of lost track of what particular amplitudes you were talking about, what particular stars were they?
What I am saying is that the slope of the loop that the variables perform in the instability strip is changing when you move from the blue region to the red region.
Right.
And so there is almost no possibility for all of them to approach the same limit at minimum in a specific region of the instability strip.
Okay, well, that would depend on whether your target is the horizontal branch or whether the horizontal branch in some color is also sloped. And that would then introduce an amplitude dependent change for that particular wavelength and still preserve a minimum which has low scatter. I would like to sit down with a piece of paper with you.
Yeah, good point.
Thank you.
Thank you for the question, Giuseppe. We have a few questions here. You had your hand up, Andrea. Did you want to ask?
I just wanted to respond to Horace's comment about the period changes to see if there's a change with the different Osterhoff groups. Alistair and I worked on a paper a couple of years ago using RLR stars and IC4499 for that purpose. And we found it was really difficult. Most of them were the bombs, Horace. And like if you look at the individual stars, it was really hard to find period change rates that made sense for like to use them for evolutionary statuses. They looked like they were pretty chaotic. But you can take a look at our paper. We had tried to do that as well.
Yes, I remember your paper. I'll have to go back and look at it.
Yeah, thanks.
Yeah, I'm just curious because in the way this kind of sets up the Sturge's law as a fundamental anchor, and I have no quibble with that, except that it, as far as I know, it's a completely empirical rule. Is there ever been a physical explanation for why this should be? I'm fishing here. I mean, yeah.
I'm not going to push back, but we've been hearing that minimum has all sorts of curious low dispersion aspects to it earlier today. So to the degree that we're seeing it coming over and over and over again, it may lead some credence to it. And it doesn't have to be dispersionless. It just has to be of low dispersion. And so there's going to be some scatter in there. But so,
To your knowledge, there is no physical.
well, I think no, but I think the problem is that Sturge's law has been used by people to get reddening, and then it's over. And theorists aren't necessarily being informed or realizing that there is something to be explained in Sturge's law. So, hello.
One last question
Maybe
in the
one.
back. I'll just take it back. real quick. One last question in this talk.
Thank you very much for this very revealing talk. It was very interesting. I just want to add a few more dimensions to your plot that because so far you haven't mentioned metallicity in this relationship, but of course there is also an evolution of the light curve shape together with the amplitudes as you go for inside the monometallic population. And that will have to be taken into account as well, of course, if you are trying to measure distances, for example.
I think you should.
This is more of a comment than a question. Oh.
Hold on. You need this.
That's it. Okay, you can look up epiphenomenal in Google. I believe that the metallicity is along for the ride, that it is not causal in this, but it is there for whatever reason. The metallicities are what they are across the instability strip and across the horizontal branch. They don't seem to make any sense that the stars that are in the red part of the instability strip have the highest masses, therefore had the lowest mass loss rates and have the highest metallicity. So metallicity is not driving in any obvious way the mass loss. So you do have a spread of metallicity, you do have a spread of apparent metallicity, and you do have a spread of mass. But I think that the marker that's on each star of its metallicity is just riding along with its temperature evolution as a function of mass.
All right. Thank you very much, Barry. Is it a quick question, Avi?
Yeah.
Or a quick comment?
So there are RLIs in dwarf spheroidals
Yeah.
that aren't Oosterhoff 1 and
No,
nor
they're
Oosterhoff 2. So that is actually lends credence to your interpretation that metallicity is along for the ride and that there's something else that's changing.
Yeah, it's always a problem to sort out all of these things when they don't meet your expectations. But thank you for that point.
Thank you, Barry. Let's thank Barry one more time for a thought-provoking talk.